It's not working. Oh, it is working. So we're going to go ahead, we did 6, okay, and we're going to do 7 now. And then tomorrow we are going to do the second lab. Now, looking at the labs we're going to do, actually the third lab finally in here is going to be the 5th lab in your lab manual. So make sure you do the right pre-lab and all that. Tomorrow's lab, so what does IMF stand for? Intermolecular forces. I like tomorrow's lab. It's potentially short again, so I apologize in advance for how potentially short it is. But there will be, need to do a lab report and everything for tomorrow's lab. And the data you collected last Thursday, that report is due tomorrow. And the way it works is, if you're running late, remember you can get it to me Friday-ish even, and it's still on time. Okay, but not like Friday at 5 p.m. But you know. Cool. Well, I'm going to go ahead and I have a handout for this. This is what you know how textbooks have like things in the inside of the textbook, like your periodic table or something like that. My organic chemistry textbook, like how many years ago, actually had this on the inside cover. And my maiden name was Newton, so it makes me smile. This is a piece of history here, people. So I want to go ahead and take a stab a little bit at this is my organic chemistry book. So actually today I want to talk a little bit about organic chemistry. The difference is general chemistry is inorganic chemistry, and this is organic chemistry, but we kind of dabble in this. The difference is that inorganic chemistry, well, it's easier to say what organic chemistry is. If you look at a periodic table, basically organic chemistry is to take carbon, nitrogen, oxygen, some of these key elements, and to connect them together. That's organic chemistry. Now, why we need to worry about it is this idea of how they bond to each other. So you need to know a little bit about something called functional groups in organic chemistry, and that's what the sheet I just gave you is, functional groups. So in order to understand kind of a little bit of functional groups, we need to understand structures. Our options for displaying a molecule, okay? We have some options. We can draw the Lewis structure. We've dabbled in that, okay? We can draw something. I have an example to show you these. A Kukule structure, okay? We can draw a structural formula. And again, it's easier to kind of show you the differences, but you can read the differences there. Alternatively, we can give a semi-structural formula, a condensed structural formula, or a line formula. And each one of these have their benefits. And again, it's easier to show you. I'm not going to have a test question about draw the line formula of blah, blah, blah. Okay, but I'm going to show you an example of it. And actually, it might make more sense now, like when you read my answer keys, like, oh, that's what she did there. Okay. We already talked about these two with regard to formulas. We have the molecular formula, the real number of atoms of each type of element that are in that repeating unit. And then sometimes molecular formulas can be reduced to empirical formulas. Remember, empirical formulas like the empirical formula of H2O2, hydrogen peroxide, is the Santa Claus formula. So I think this needs to go away. This one's drawn. Yep. Oh. Yep. So H2O, hydrogen peroxide, H2O2, hydrogen peroxide. We can reduce it. That would be the molecular formula, and the empirical formula is this. So this is the Kukule structure. Okay, it looks good. Notice that, and I'll be kind of using these terms, the carbon chain is 4 carbons long. Carbon chain. Okay, with hydrogens all around. We could write that a different way, and sometimes you definitely wouldn't want to write it that way. For instance, these all mean the same thing. So here you see the 4 carbons, okay, but you kind of see this group is this group, these 2 groups are these 2 groups, and this is this group. Okay. We could go ahead and it's kind of like math. We could say that I need 2 of these in that formula, structural formula. I've used the word unpack in here. It's kind of like if you're given this, you kind of have to think this. Okay, if you're given these down here, think of that this is really what it is. What is it? Well, it's basically, we have our 4 carbons, 1, 2, 3, 4, and we have hydrogens spreading around them. One of the things we talked about in Gen Chem 1 is that carbon likes to reach out 4 times, 8 minus the group number, the group number of carbon is 4. So that's why actually this is really a messy slide, but you're going to see as we look at this, think of that, carbon's going to reach out 4 times in a neutral molecule. All right? This is a line formula of that same thing. Like, are you serious? This one, people who like to be abbreviated, this is the route to go. The way you look at the line formula is at the beginning, or at the end of each segment, think of a carbon. So there's a carbon there, carbon there, carbon there, carbon there. And then the other thing about a line formula is they assume, like I said a minute ago, that you know that the carbon's going to reach out 4 times, and what's not shown on there are hydrogens. So you have to kind of say, well, if this carbon's connected, that's a bond between those 2 carbons, then that's 1, 2, 3, 4, okay? This is reaching out twice to 2. It's 2 carbon neighbors, it needs 2 more, okay? And so sometimes actually on my answer keys, I kind of do just dashes to show you, hopefully you guys know that there's hydrogens at the end of there, then there are dashes. Okay, so these all 4 mean the same thing. How cool is that? Pretty cool.
In the line formula, does the end of the segment always have to be a carbon?
For the line drawing, yes, the end is going to be a carbon. Now, if there's an oxygen drawn there, it's not a carbon. So does that make sense?
Yeah.
If there's nothing there, it's a carbon. But if there's another element there, it's not like it shares it with a carbon. It's like that is what it is. So let's take it up a notch. One of the things, I'm just going to kind of dabble in this idea of, one of the things in organic chemistry is we name compounds. And I won't be doing too much, but to name compounds, you look for the longest way to get a carbon chain. So I had 4 carbons before. Now we see a little bit of branching here. We've talked about branching here. So I can get, this could be my carbon chain. I got 1, 2, 3, 4, 5, 6. 6 carbons, and actually 6 is going to be hex. So let's type a hex in the name. The branching there at carbon number 2 and carbon number 5. But that's not what I'm trying to talk about right now. Now, we could rewrite that. So it's got 6 long ones, and here it's got a branching, and here it's got a branching. Okay. We could rewrite it. This means the same thing. By the way, anytime you see CH3, that is what we call a methyl group. Methyl. Don't go there, methyl. No. So CH3 is a methyl group. So we have 2 methyl groups here. That would represent these 2 guys. And then you have your CH. There's your CH. And then you have your CH2, CH2. Then here on the end, it's kind of fun because you have your carbon. And it's got, what, 3 methyl groups. So, isn't that fun? No, right? So I don't know if that's where I stopped. Changing it up a little bit. Now, this hydrocarbon contains only hydrogen and carbon. That's what we've looked at so far this afternoon. This one has oxygen. I think we talked about, when we did combustion analysis, you can do combustion analysis with hydrogen and carbon, or you can do combustion analysis with organic compound that has oxygen. Okay, so here we go. This would be the Kupele structure. This would be the structural formula. So hopefully you can kind of see where things are. CH3, the CH2, here's the carbon, double bond oxygen, single bond OH. So I told you CH3 is a methyl group. This right here I'm going to tell you is a hydroxyl group. The cool thing with hydroxyl groups is, guess what? You can have hydrogen bonding. Isn't that awesome? Hydroxyl groups equal hydrogen bonding. And actually, that's one of the reasons why we're kind of dragging ourselves through this sort of different sort of functional groups. That's a structural formula. And this kind of goes back to, yep, what we were talking about. Yep. So we would put a carbon here at the end, a carbon here, a carbon here, and then over here, notice that that is this guy right here. That's the hydroxyl group. So how many carbons in the carbon chain there? I just got 3. Yeah. We got room on this slide. No, I'll go ahead and do it. Well, I'll wait. I think I might have it later. Okay, cool. So those all mean the same thing. And here in a minute, I'm going to actually call that a carboxylic acid. All right, so hydrocarbons contain only hydrogen and carbon. So we've done a lot in here about looking for like a polarity, right? And so to find polarity, you look at the electronegativity differences between the two atoms that are joined together. So on the Pauling scale, we've just got a difference of 0.4, which is kind of puny. Not to say that it's entirely nonpolar, but in general, hydrocarbons, carbon and hydrogen, the only thing in their structure, are nonpolar. Hydrocarbons are nonpolar. Yep. I have weak or best weakly polar. Okay, so there's that. So now, let's see how I'm going to do this. So on the sheet I gave you, find alkane. The sheet I gave you, it just says RH. It's alphabetical, so it's kind of at the top. Alkanes. So the R means any functional. R means could be represent anything, and it's bonded to an H. Alkanes are examples of hydrocarbons, and they have only single bonds. Only single bonds. I don't know if that will be significant, but you never know. So now we see a prefix. If you have a carbon, I think I'll put it on the board. If you have a carbon chain of 1, like that, your prefix is going to be NETH. So carbon chain. And this is prefix. So 1 is meth. It's meth and it's an alkane, so it ends in ane. So methane. That's it. Okay. 2 carbons is F. 3 carbons is prop. And 4 carbons is bute. So here we have 4 carbons, all single bonds, butane. Whoa. Okay. I think we looked at this one. No, it's a little different, isn't it? Now, in order to name this, we're going to look for the longest carbon, and that's what sort of ane it's going to be. To me, I'm liking this right here, the longest carbon chain. Notice that I could go this way or I could go this way, and actually you're going to get the same thing. So we're going to go with the longest chain. We got 1, 2, 3, 4, 5, 6. So 5 is pent and 6 is hex. 7 is hept, H-E-P-T. What's 8? Oct. Yeah. I think 9 is non, I think, N-O-N. I think. What's 10? Deck. Yep, you got it. Yep. So you look for the longest thing, and so we're getting 6 carbons. So it's going to be a type of hexane. But now the other thing is we need to name these branches. And the trick for naming branches is you want the lowest number. So we include the number where the branches occur. So if I were to call this carbon 1, 2, 3, 4, 5, 6, then I'm going to have what? My methyl groups would be on carbons 4 and 5. But if I start here and call this 1, 2, 3, 4, 5, 6, now my branching is on carbon 2 and 3, and that's preferred. So I'm going to show you what I mean. So I'm going to start from right back to left again. And I'm going to literally call this carbon 1, carbon 2, carbon number 3, my longest chain. And then I know it's a hexane because that's 6 in my longest chain. And my branching occurs at 2 and at 3. So that makes this 2, 3 branching. Di means 2, and these are my methyl groups. So those are my methyl groups. 2, 3 dimethylhexane. That's it. That's it. Correct. On that aspect of meaning. So is this all single bonds? No. Carbon chain, I'm liking 3. Now this actually is an example of an alkene. So I bet that sheet I gave you has alkenes. Yep. Alkene has R2, C, double bond C, R2. So all this is telling you is you have a double bond within your carbon chain somewhere, and it's an alkene. That's it. Okay. Now, if we have more than 3 carbons, we're going to have to tell where the double bond is. So that's propene. Let's look for the longest chain. Looks like 5 carbons. Again, I could go up this, and I could go this. I could go up. I could go north, or I could go west. Excuse me, go north or east, and it's going to be the same diff. So I got 5. So that makes it a pentene. Now I need to do 2 things here. I need to say where the double bond is. Okay, and notice that if I make this carbon 1, carbon 2, 3, 4, 5. My double bond is here between the 2 and the 3. That's where that 2 comes in. That 2 right there. And my branching is also on the second carbon. So that's it. 2 methyl, 2 pentene. That's it. Ooh. Let's look for the chain. I got 4. So that's why it says butene. This is a little different. I need to say where the double bond is. And the double bond is on carbon 2, 2 to 3. Oops. So that's where that is. And actually, we're going to be talking about this more soon. This idea of trans. The opposite of trans is, maybe it's on the next slide, I don't think so. But the opposite of trans is cis. Okay, see if you can, I feel like a cheerleader, okay? Trans is like, rah, rah, yeah, I've got pom-poms here. Trans is like this, okay? And cis is like this, okay? Okay, trans, cis, that's it. So anyway, this is a trans. And the reason it makes a difference is, and I don't think I barely maybe mentioned this in Chem 1, but if you have a double bond there, you can't rotate it. It's stuck. It's actually, this would be kind of like a planar molecule there at the carbon double bond. carbon double bond carbon and carbons and hydrogens. That's stuck. So anyway, trans are 6. What else we got? Oh, we've talked about this guy for a while. This is C6H6. This is benzene. Now, if I say something is aromatic, you probably think, oh, something has some aroma to it. Now, the reason something that's aromatic, be careful, because that means that those molecules are getting in your nose. And if it's deadly, you're going to die. No, I mean, honestly. But aromatic means that probably has low intermolecular bonds. Okay? So this is C6H6. This is benzene. So, I think I might have said this before. I don't know. But a cool thing about this alternating double, single, double, single, double, single bond between that ring structure, those 6 carbons, is that they form 2 very important resonance structures. Resonance structures are basically where you have the double bonds drawn. So instead of single, double, single, double, single, double, it's single, double. Instead of double here, it's a single here, and it goes around. 2 important resonance structures. Okay, both awesome. So it kind of goes back and forth, and it forms a very stable pair of structures. We call it resonance structures. So anyway, to draw, oftentimes benzene is a really common nasty thing. You'll see it drawn like this, where actually that circle in there is kind of showing you those pi electrons that are what we call delocalized. That's what delocalized. Kind of running around. So that's benzene. Benzene's a good thing, say very reactive, and oftentimes you can kick off a hydrogen and stick something else there. So I'll just give you an example. Meet toluene. So toluene is C6H5, and one of those carbons have been kicked off, and we have a methyl group there. That's toluene. Fancy name for benzene with a methyl group on it. Naphthalene, 2 cute little cozy benzene rings. Okay, so some of those were hydrocarbons, contains only hydrogen and carbon, nonpolar. You throw an oxygen in the mix, and you have a degree of polarity there. Okay, so we're going to talk about some compounds, not alkanes, not alkenes, but other general compounds that have oxygen in them. So go one step further. Let's just say, and it happens a lot, that your compound has a hydroxyl group, the OH. Well, dang it, then you can go ahead and hydrogen bond. But if it just has the oxygen, at least you have like a little polar group there. Okay. So here we go. And I don't know, I think I'm going to show you, these names are actually here. So generally, you've heard of alcohols. They have a hydroxyl group. Phenols, carboxylic acid. These are all things that have a hydroxyl group. These things listed here, ethers, aldehydes, ketones, and esters, they have an oxygen, but that oxygen is not bonded to a hydrogen. So you see on this slide that the families are members of those families of compounds then will not hydrogen bond with themselves. All right, so ethyl, 2 carbons, okay, ethyl alcohol. Alcohols have an OH group, and the sheet I gave you has alcohol on here, and you will see ROH, where R can be anything, and OH is OH. Okay, ethyl alcohol. This is an example of what we call a diol. It's got 2 hydroxyl groups. Okay, this is ethylene, ethylene 2, glycol. I'm not sure glycol is a standard name. See the benzene ring? Okay, instead of one of the hydrogens kicked off, we have a hydroxyl group. Welcome to phenol. Acetic acid. Acetic acid is an example of a carboxylic acid. So if you look under C's for carboxylic acid, you'll see your, let's try to get it right. you'll see your R, C double bond O, and then also kicked off of that O, you have an OH group, hydroxyl group. That's a carboxylic acid. And acetic acid is an example of it. Carboxylic acid. But what these all have in common is they can hydrogen bond with themselves. Now, again, on your test, you're not, or for homework even, you're not going to have to name these things, but you're going to have to look at them like, oh, I see an OH. I bet it can hydrogen bond. Now, we have an oxygen here, but it's not a hydroxyl group. This is a first example of an aldehyde. So if you find aldehydes, you see the R, C, double bond O, and H. It's kind of like it's what I call more of a terminal thing. Aldehydes are terminal. Notice we have 3 carbon chains, so it has the pro prefix. Propionaldehyde. So can this hydrogen bond with itself? No, cannot. Nope. If your double bond oxygen is kind of in your carbon chain, it's not an aldehyde, it's a ketone. Okay. So this is aldehyde, the word aldehyde, and this is an example of a ketone, where, like I said, the double bond oxygen is in the chain. This is an example of an ester. Yep. If you find ester, you're going to see what makes it an ester is this. In the carbon chain, we have a double bond oxygen, and that same carbon in the carbon chain has an oxygen embedded in it. So that makes it an, did I say ester? Oops. Esther, get over here. Sorry. Okay, and this is an ether. So we have esters and ethers. Ethers are R bonded to an O, bonded to another R group, basically. And I think in the sheets, a lot of times they'll say R and they'll call it another one R prime, because they definitely don't have to do the same thing. Amines, if you ever hear the word amine, hopefully you're thinking nitrogen. Amines all have nitrogen. And we actually have 3 options for amine. We have a primary or secondary amine. Primary has a 1 with a little superscript 0. Secondary is a 1 with a little superscript 0. Now, remember when we talked about hydrogen bonding, a lot of times I have to pull the periodic table. Hydrogen bonding, we know that it's hydrogen bonded to an oxygen, but it also could be hydrogen bonded to a nitrogen or hydrogen bonded to a fluorine. So those 3 together, hydrogen bonding. So actually, we have potential for hydrogen bonding with amines. So here's an example. We have a 2-chain, it's F, okay? And our mean functional group is right here. This guy right here. Now, hopefully you're keeping in mind what we talked about earlier today. When you see the NH2 all balled up, hopefully you can kind of unpack it and think of that nitrogen with those 2 hydrogens squirting away, branching off. That's that nitrogen. This is actually what we call a primary amine. This one is primary. And what makes it primary is that actually, how do I say this? Actually, it only has, primary meaning 1, it only has one thing that's not a hydrogen. This is what makes it primary. Let's look at a secondary. Now, in this one, again, you kind of have to unpack this particular structure, but notice we have this hydrogen is kicking off the nitrogen, okay? And we have these 2, these are called methyl groups, right? Those 2 methyl groups. So now we have 2 things that aren't hydrogen kicking off the nitrogen. That makes it a secondary amine. Okay. But we can hydrogen bond over here, and actually I think sometimes we have we have questions about the degree of hydrogen bonding. Does this make sense? That we have more sites to hydrogen bond in a way here, and we have fewer. We have more bang for your buck with a primary. Secondary, no, they want more. I mean, you have less. Okay, we have an extra one here with the primary. We have 2 here, 1 here. Well, here's a tertiary mean. Tertiary, of course, means 3 with a superscript. And it looks like this. So tertiary means that they have 3 things that aren't hydrogen bonding to that nitrogen. And it only, so here's the nitrogen. Now, can you guys see why it can't hydrogen bond? Why can't it hydrogen bond? There's no available hydrogens. Yeah, exactly. Cannot hydrogen bond. Poor thing. So now this actually goes into some of the things that we've talked about. Hopefully this will all kind of sound a little bit familiar. We talked about when you increase the molecular weight, which of the intermolecular bonds increases with increasing molecular weight? You can use whichever name you want to say. Dispersion forces. Yep. Dispersion forces increase in general. So if you have alcohols, the dispersion forces will increase with molecular weight. And then the other thing, you see where actually we're kind of mixing something we've already talked about. With increased dispersion forces, higher boiling point temperatures. Okay. Alcohols and ethers. Alcohols and ethers. Again, you don't have to remember this. Okay, but ethers, if you find it on here, ethers are the ones that have the oxygen embedded in the carbon chain. So why do alcohols boil at a higher temperature than ethers?
The hydrogen bond?
Because the hydrogen bond. Yep, because the hydrogen bond. Don't you gonna say 2 and 3?
Yeah.
Mm-hmm. Exactly. And so you could actually, is this right? I think it is. Isomeric, you can actually have the same atoms of each type of element in both compounds, but it's just arranged differently. One case you have an ester, or excuse me, an ether, and one case you have an alcohol. Okay. Boiling point increases as the number of carbons increase. To me, that's kind of like a molecular weight thing. Okay. Branching will lower the boiling point temperature, and again, this kind of goes back to the other day I kind of wrote down over here kind of how you try to pick apart what sort of intermolecular bonding they have. Branching is an element, branching balls it up, so you have less opportunity for dispersion forces. And so that means then it'll be weaker, your dispersion force will be weaker, so your boiling point will be lower. Boiling point will increase with increased numbers of hydroxyl groups. Remember hydroxyl, think OH, so you can have hydrogen bonding. That makes sense. All right. Solubility. Like dissolves like, right? Okay, so with that in mind, let's see how this works. If you have an alcohol, that means that you have carbon chain, and then you stuck in a hydroxyl group. I already told you that. Think of that carbon chain as being nonpolar, but dang it, the hydroxyl group is very polar. So you kind of have a confounded sort of situation with an alcohol as a polar end and a kind of a nonpolar end. So this says that if you go ahead and make your carbon chain short, guess who takes over? The hydroxyl group. So if your alcohol has 3 or fewer carbons, then it's going to behave, your hydroxyl group to take over. It's going to behave like a polar molecule, and it will be soluble in water. Like dissolves like. Water is polar. Now you have something that's polar. If you add more carbons there, then it's not going to be soluble. Then the tipping point is 3 to 4. If you go ahead and add now 4 carbons instead of 3 carbons, now you have increased the nonpolar part of your molecule, and you go to try to dissolve it in water, and it's like, dude, I am non-polar. So it's limited solubility. Or, of the four, oh, there is one, sorry, there are different forms. The N-butyl is insoluble, but if you ball it up, tert-butyl is soluble. Sorry. Above 4, solubility in water decreases. So here we've got kind of some different criteria. We have one carbon, and from that carbon we can branch 4 hydrogens. We can branch 3 hydrogens and a chlorine. We can branch 3 hydrogens and a hydroxyl group. This is kind of the corresponding name, melting point, boiling point, and how soluble they are in water. So why is methane so much less soluble in water than methanol? Methanol. Like dissolves like. Yep. So this guy is polar, water's polar, that guy's polar. Methane is nonpolar. Yep. So it will not want to dissolve in water, but infinite solubility means that, like what it says, definitely dissolves. So there's those 3. And then there's these 3 right here, which again, we're kind of taking some sort of ethane group and we're putting a hydroxyl or a carbon or another hydrogen. And then this one, propanol, and then this. They all just I kind of grouped them like that because they're trends that we talked about just this afternoon. This is what I was describing a minute ago. If we have a 1-carbon alcohol called methanol, this is your carbon, hydrogen, 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 and this is your OH. Okay, so philic means to love. So this guy here is hydrophilic, this guy here is hydrophobic. Why? Because this is polar, this is the polar end, and this is the nonpolar end. So, like I was saying, if we go ahead and I can see we're increasing from 1 to 5, okay, so now we have 5 carbons here with their associated hydrogens. We have basically increased the nonpolar part, and this is water. Phobic means hate. It's a hate water, so it's not soluble. So I mentioned butanol and tert-butanol a minute ago, and anytime you see the word 1 with an alcohol, or sometimes it'll say N for normal, N-pentanol, 1-butanol, or yeah, N-pentanol, 1-pentanol, they mean the same thing, that basically it's just one long chain, no branching. That's an N, not an H. That means no branching. Hot dog shape. So this is a mixture. You kind of have to look carefully for our H2O molecules and our methanol molecules. So for instance, I'm liking this for H2O. Okay, all this is H2O, and water kind of does this hexagonal thing. And then over here we've got this is our methanol. So this is our carbon, hydrogen, and then this right here, no, sorry, this is oxygen and hydrogen, and then this right here is the methyl group. So that's methanol. So anyway, we definitely have a mixture here, and you can kind of see the methyl groups of the methanol connecting up with the water groups, because that's the water loving part. I love that water. So hydroxyl groups are OH, the word poly means more than one OH. So I mentioned diol here in a minute. Anything that has more than one OH is a polyhydroxyl. Okay, and they give more regions for hydrogen bonding. So they will have higher solubility, higher boiling point temperatures. So now I kind of we didn't cover this one yet. This is a carboxyl. So if you find on your sheet carboxyl, you'll find R, carbon, double bond O, and then also the carbon has a hydroxyl group. So carboxylic acids or carboxyl groups, carboxylic acids, anyway, they can hydrogen bond. Okay. And so we see that they have more going for them, if you want to call it that way, than do alcohols. Why? Because they also have this partially negative region. And then ketones don't have a hydroxyl group. Ketones are aldehydes. So carboxylic acids rock. So they would generally have higher boiling point temperatures and higher melting point temperatures compared to their analog alcohols, ketones, or aldehydes. You're almost done? I think we're almost done. So carboxylic acids, again, they kind of have the terminal carbon going for them, and the carbon has a hydroxyl group, and the carbon also has a double bond oxygen. So they can hydrogen bond with water, they can hydrogen bond with themselves. If you go ahead and add too many carbons onto that R group, then again, it's like we saw with alcohols, you're building up a hydrophobic end, a nonpolar end. So then it has limited solubility with carbon within water. Carboxylic acids, generally like alcohols. Don't we all? I'm just kidding. So again, anytime with any compound, if you start to increase the number of carbons, called the carbon chain, then it becomes more and more nonpolar. And like this says, then if you're looking for a solvent to dissolve it in, you better go to a nonpolar solvent. And it'll work just fine. Ketone, right here, if we have kind of group right here, like another carbon, if one of these is a hydrogen, then it's an aldehyde. This says with regard to ketones and aldehydes, they don't have they have, depending upon how much other carbons we have, they're generally nonpolar. I feel like we've kind of beaten a dead horse here. You add carbons, you can increase the dispersion forces, and then you can increase the boiling point temperatures. All right, again, back to the amines. Hopefully we're all on the same page. Amine, think nitrogen in your formula. Listed from left to right, we have our primary, which is like this, secondary, which is like this, and our tertiary amines. Which one of them cannot hydrogen bond? Tertiary cannot, exactly. Amines are moderately polar substances. Primary and secondary can hydrogen bond to each other and to water. Tertiary cannot hydrogen bond to each other or to water. Oh, tertiary cannot hydrogen bond to each other, but can hydrogen bond to water. Think about that. Okay. Oh, I just ran out of it. Good thing it was almost to the end. So, any questions? Okay, so live tomorrow, and then on Friday we'll come back and pick up part 5. I promise.